Okay, let's go for the next topic, and that's gonna be Kirchhoff's rules. We use Kirchhoff's rules mainly when we have two or more batteries in a circuit, like in this case. Correct? We have a circuit and we have three batteries. Okay, and we have these two rules that we use for solving these types of circuits. Correct? We have the junction rule. A junction is a point where two or more branches meet, or currents, let's say, meet. Correct? And it says that the sum of all the current going to that junction must be the same as the current leaving that junction. Or we can use our charges, right? All the charges going into that point junction is leaving that junction. This is the conservation of charge, this rule. And for example, imagine that we are taking this to be current 1, and imagine that current 1 is split into current 2 and current 3. So this junction says what? This rule says that current 1, let me do it here, current 1 is equals to current 2 plus current 3. Okay, the direction and junctions are optional. We can go in this way. We can call this current 1, 2, and 3. Or we can go in this direction. We can call this current 1, 2, and 3. Or in this direction, 1, 2, and 3. It's optional. At the end, current must be positive. If we get the value for the current to be negative, it means that the current goes in opposite direction in that branch. Okay, perfect. So that's again junction rule. Let's go to loop rule. Means that we're supposed to make loops. We can make loops clockwise, right, or counterclockwise. Let's make it right here clockwise. We can call this loop 1, and we call this loop 2. Correct? And we have these rules across the battery. If the loop goes from negative to positive, the voltage drop is positive. If the loop goes from positive to negative, the voltage, right, is gonna be negative. Now, when we are across a resistor, if the loop, this is the loop, if the loop goes in the direction of the current that we choose from the beginning, right, then the voltage drop is gonna be negative. If the loop goes in opposite direction as the current, then the voltage drop is positive. Correct? For example, this is again the junction rule. What about for loop? Let's call this loop 1, right? This is loop 1, and this is loop 1, and this is loop 2. Okay, perfect. For loop 1, let's apply these rules. For example, imagine that I'm starting on this value, right? So I'm going from negative to positive, right? From negative to positive. How is the voltage drop? Positive, right? So what do we have? This is 2 volts. We don't use the unit, just the quantity. Okay, perfect. And then let's go. We're going around, right? And we are right here. The loop and the current are parallel, right? When the loop and the current are parallel, the voltage drop is negative. Gonna be negative. In this case, we just we use the Ohm's law, right? Voltage equals to current and resistance. So the voltage drop is 2 times current 1. Okay, perfect. Let's continue. In this case, right, the loop is going around and meet the second battery. Again, goes from negative to positive, right? From negative to positive, the voltage is positive, plus in this case 4 volt. Okay, now we are right here, and if we're taking this current 2 going down, and in this case the loop is going down too, so they're parallel. When they're parallel, the voltage, right, is gonna be negative, minus in this case for current 2. Correct? What else? Now we are right here. Again, this current 1 is from here to here, right? This is current 1. This is current 2 only in this section, and current 3 goes from here to here. Correct? because we have another loop right here. Look, it's gonna be current 2. This is coming in this way. Current 3 and continues right current 1. Okay, perfect. Now one more time, current goes in this direction, the same thing as the loop. So these two are parallel. These two are parallel, the voltage drop is negative. It's gonna be minus what? Minus 4 current 1 equals to what? What do we have right here? Equals to, I forgot to write the conclusion right here. It's gonna be the sum of the voltage drop is equals to 0. Okay, this is a loop rule. Great, it's gonna be equals to 0. And well, we can work with this. We can say this is 6, right? 6 minus 6 current 1 minus 4 current 2 equals to 0, correct? Okay, let me see if it's correct. Okay, it's gonna be 6, correct, negative 6. It looks like it's fine. Okay, equals to 0. Now let's go to loop 2. Loop 2, perfect, the same thing. This is loop 2. We can start, let's start with this battery, right? So it's gonna be, the loop is coming from positive to negative, right? From positive to negative. How is the voltage? In this case, it's gonna be negative 4, right? Negative 4. Perfect. Let's go around, emit this battery. Look, the loop goes in this direction and the current also goes in that direction. They're parallel, right? When they're parallel, the voltage drop is negative through the resistor. It's gonna be minus what? Minus 3 current 3. Perfect. And then the loop is coming and now meets the, let's say the third battery. It goes from positive to negative, right? From positive to negative through the battery, so the voltage is negative, minus 6. Great. Okay, whatever. Okay, it's coming. Now meets this resistance, but in this case, look, the current goes in this way and the voltage goes as the loop goes in opposite direction, right? When they're opposite, like in this case, current and the loop opposite, correct? So the voltage drop is positive, plus 4 current 2 equals to 0. Let's see if we can reduce this equation. So this equals to negative 10, correct? Minus 3 current 3 plus 4 current 2 is equals to 0. Okay, as you can see, we have three equations and 3 unknowns, right? We have 1, 2, and 3 equations. Okay, we can, for example, reduce this to these equations. We have negative 6 current 1 minus 4 current 2 is equal to negative 6, correct? This one. We can make this positive, right? Positive, and positive. Okay, perfect. The third, this is the first one, second. The third one, what do we have? The same thing. It's gonna be negative 3 current 3 plus 4 current 2 equals to 10. Okay. For example, let's substitute this value, current 1, right here. And what do we have? Well, we have now this is 6. Okay, this is 6. 6 times current 2 plus current 3 plus 4 current 2 is equals to 6. And the other, the second one stays the same, right? 33 current 3 plus, well, before that, look, we can work with this one. And what do we have? It's gonna be 6 current 2 plus 4, 10, right? 10 current 2 plus 6 current 3 is equals to 6. Perfect. Now, what do we have? In this case, we have, look, 2 equations and 2 unknowns, correct? We have then 10, look, we have 10 current 2 plus 6 current 3 is equals to 6. Is that correct? And we have also this one's gonna be 4 current 2 minus 3 current 3 is equals to 10, correct? This one. Okay, now we multiply, well, let's cancel current 3, right? Current 3. To do that, we multiply this by 3, correct? Or multiply that by 3, what do we have? What's gonna be 12 plus 10 is gonna be 22, current 2. This is cancelled, and then we have 30 times 6 equals to 36. From here, current 2 is equals to 36 divided by 22. And what is this? This is equals to, you have a calculator. Let me find my calculator. I found it. Oh my God, somebody move it. Okay, perfect. Now, what do we have? It's gonna be 36 divided by 22. Oh my God. Let's say 6.64. Okay, around 6.64 amps. Okay, amps. So, and it's positive, right? It's positive, means that this is correct. This direction is correct. Great. Now let's find the other currents. We can find, for example, current 1 from here, correct? So current 1, or we can find current 2 right from here, because current 1 is right here. Okay, current 2. What should be current 2? Current 2 is equals, oh, we found current 2, not current 3. Perfect. Current 3, because it's current 2. Current 3 is equals to 6 minus 10 current 2 divided by 6. Okay, let's find it. Equals to, okay, 6 minus 10 times that quantity, correct? Okay, divided by 6. Okay, perfect. Equals to negative 1.73. Negative 1.73. Correct? Amps. Means actually, look, this current is gonna be how? In this direction, right? We guess right in that way, but we found from the calculation gonna be opposite. Perfect. Now let's continue. What about current 1? Okay, current 1 is equals to, what is current 2? 1.67, 64, right? Amps minus, okay, minus, blood is minus right here. Okay, 1.73 amps. Okay, what is the answer? The answer is gonna be, okay, plus 1.64. Okay, gonna be negative 0.09. Negative, okay, 0.09 amps. Negative. Means what? Well, this is with these steps we calculate, right, the magnitude and also the directions. In this case, means that actually the right direction is gonna be this one. Okay, it's gonna be current 3 in this direction, current 2 is correct, and current 1 goes in this direction. Right? That's the right direction, and it makes sense, right? Because this is the strongest one, correct, and dominates on the rest. Got it? And again, this is the way how we applied Kirchhoff's rules to circuits where we have more than one battery. Okay, perfect. Now let's go to the next topic. The next topic is capacitors in series and in parallel. Let's do the same thing as we did for resistors in series and in parallel. Okay, great. Let's do it. Okay, now imagine that we have these capacitors, right? So we have capacitors in series and in parallel. Capacitors in series and parallel. In series and parallel. Okay, perfect. Let's go to series. So imagine that we have this this battery, correct? And then we have this a battery, right? This is positive, negative, this is electromotive force. Okay, perfect. So we have capacitor 1 right here, another capacitor right here, correct? And another capacitor right here. This is capacitor 1, 2, and 3. Correct? Also, we have charges, right? This is positive charge, negative charge, right? Positive charge, negative charge, positive charge, negative charge. Okay, look, in this case, what do we have? The same thing as for a resistor, right? The voltage drop is the same as the sum, right? So we have the electromotive force is the sum of all the voltage drop. Remember how to when we're dealing with capacitors, what is the formula that helps us? We found that the capacitance is equals to the charge divided by the voltage. Correct? We found that before for capacitors, right? And then because we have right here the capacitor and the charge, what do we have? Well, remember, if we solve for voltage equals to capacitor divided by the charge divided by the capacitance. So we have this ratio right here, and that'll give us this voltage drop, right? The same thing right here, a voltage drop and voltage drop. So we can call this voltage drop 1 V1, this give us V2, and this give us, right, V3. The same thing as for, similarly, as resistors, right? So the total electromotive force equals to voltage drop 1, 2, plus 3. Okay, but what is the voltage drop? One more time is gonna be charge, right? Divided by capacitance. We can take charge 1, okay? Charge 1, right, 2, and 3. But the charge is constant, okay? In series, charge is constant. The charge is constant. Okay, so what do we have then? This equals to charge divided by capacitance 1 plus charge divided by capacitance 2, right? Divided by capacitance 3. Okay, because the charge is constant in series, correct? What do we have? Well, again, we can use 1, 2, and 3, but it's constant. So we can factor it out. It's equals to 1 over C1 plus 1 over C2 plus 1 over C3. All right, when we compare this to the general equation, remember this is the equation when we have voltage in general, but also we can use when we have the electromotive force. In this way, electromotive force is equals to the charge, the capacitance actually. Capacitance, I'm following this part right here. Capacitance equals charge divided by the electromotive force. When we compare, well, we can solve for electromotive force right here. Electromotive force equals to charge divided by the capacitance. When we compare again this equation to this one, what do we have? Well, we have that 1 over this is now the equivalent capacitance is equals to 1 over C1 plus 1 over C2 plus 1 over C3. Correct? Perfect. What about in parallel? Okay, let's go to circuits in parallel. Like in this case. Again, we have the battery. Now we have a resistor 1, resistor 2, capacitor, right? Capacitor 2, capacitor 3, capacitor, no, resistor is some resistances, correct? Why not do one example of resistance too? Okay, times of plus this capacitor 3, okay, capacitor 3 is C1 one more time, C2, C3, and this is positive, this is negative, this is, let's call it again electromotive force or voltage, correct? Now this is charge 1, charge 2, and charge 3. In this case, when we're dealing with parallel circuit, okay, parallel, the total charge is equals to charge 1 plus charge 2 plus charge 3. And the voltage is constant, right? The voltage drop are constant. Means what? Well, again, this symbol is equals to V1 is equals to, right, V2 is equals to V3. It's constant. All of these capacitors are connected to the same battery, to say this side to the same terminal, the other side to the same terminal. So they have the same voltage drop. Okay, great. Let's see what happens then. Let's go back to this equation. Right, total charge is equals to charge 1 plus charge 2 plus charge 3. What is charge 1 using the formula for capacitance? Well, remember, for capacitance, charge is equals to CV. Correct? Perfect. So this is C1V1, correct, plus C2V2 plus C3V3. But this constant, right, they're the same. So this is C equals to, we can use electromotive force times what? C1 plus C2 plus C3. When we compare, right, this to the original one, correct, which is charge is equals to electromotive force times the capacitance, correct, which is this over here, the same thing. When we compare these two, we can see that the equivalent capacitance, this is in parallel, this can call it parallel in series, correct, is equals to C1 plus C2 plus C3. Correct. Okay, yeah, we can work with one example. For example, let's say, let's find the equivalent capacitance for this circuit. Let's create something. Imagine that we have this capacitor right here. Imagine that this is 2 microfarad. We have, let's say, another capacitor right here. Let's say this is 6 microfarad. And imagine we have another capacitor, let's say 3 microfarad, right? Another one right here. Let's say 4 microfarad, correct? Imagine one more, let's say 2 microfarad, correct? And we have one more right here. Let's say what? 4 microfarad. What should be the equivalent capacitance? Let's do it. Let's start from the right to the left, and let's start with these three which are in series. When these are in series, why we use this equation right here. And then what do we have? Let's do it. So what do we have that the equivalent in series is equals to 1 over C1 plus 1 over C2 over C3 inverse. Okay, let's do it. We have, this is 1, 2, and 3. Let's do it. So it's gonna be 1 over 3 plus 1 over 4 plus 1 over 2. Perfect. I can't believe it. Okay, and then let's take the inverse. Okay, great. Equals to 0.923. Okay, so it's equals to 0.923 microfarad. So what do we have then? Look, we can draw another, the same, right? The same circuit, but we represent this one as only one. This is gonna be 0.923 microfarad, which is the equivalent for these three, correct? And we continue in this way. Now, these two are in parallel, correct? And we create a new one. This is again 2 microfarad, farad, and this is 4 microfarad, correct? And this is 6, the same, 6 microfarad. Now this plus this, we create a only one, right? Because it's two are in parallel. In parallel, we add the capacitance. And what do we have? Well, we have one more time. This is 2 microfarad. Now this one is only 1. Gonna be 6.923 microfarad, correct? And we have the next one, which is 4 microfarad. Okay, usually we label this A and B. Could be a battery right here, right? A and B. And then what do we have? Well, we have, let's say, A and we have B. And this is the equivalence, right? The equivalent capacitance. What should be the equivalent capacitance? This plus that. So the equivalent capacitance is equals to, now these three are in series. When it's in series, we use this equation. Is equals to what? Is equals to 1/2, correct, microfarad plus 1/6.923, correct. What else? Plus 1/4, right? Inverse. Everything is in microfarad. Okay, let's do it. Let's do it. It's gonna be 1 divided by 2 plus 1 divided by 6.923. Oh my God. 23 plus 1 divided by 4. Perfect. Now inverse to the -1. Okay, this equals to 1.12 microfarad. 1.12 microfarad. So that's gonna be the equivalent capacitance when we have these capacitors in series. In this circuit, not series. This is well, it's in series, correct? Okay, perfect. We do the same thing using resistors. Let's try one using resistors only. Remember, for resistors, I was supposed to use the same one, but it's fine. For the resistors, we know from the previous videos that one of the resistors in series is equals to 1/resistor 1, correct? Now this is in series, in parallel, 1/resistor 1. These are the inverse of this one. 1/resistor 2 plus 1/resistor 3. Okay, and resistance in series equals to R1 plus R2 plus R3. Let's do the same thing as the this circuit that we used before. I think was let's say R1 equals to 2 ohms, and then we have another resistor. Let's say R2 equals to 2 ohms again, and let's use this one. Okay, another one right here, similarly to the previous one, correct? And in this way, imagine that we have a battery of 10 volts. Okay, now let's get value. Let's say this is R2 equals to, let's say, 3 ohms. Imagine this is R3 equals to 4 ohms. R4 equals to to 2 ohms, and this one R5 equals to 4 ohms. To make it easier, the same thing before. When we have circuits with resistors only, usually we start with the right side, right, then go to the left side. Okay, let's do it. So these three are in series, right? When the resistors are in series, we use this property, and then what do we have? Well, we have this equivalent circuit, correct? Now this is the equivalent of these three, correct? And this one stays the same. This is R1, this is R2, and this is R5. And now it's gonna be R6, and R6 is this plus that, right? Because these are in series. That's the equation for series. So it's gonna be 6 and 3, 9, right? 9 ohms. Now, let's continue. These two are in parallel. Okay, so what do we have then? Well, we make only one, the equivalent for this one, and we call it, let's say, R7. Okay, so this stays the same. It's gonna be R1. Now let's find R7, and R5 stays the same. Okay, what should be R7? Well, these two are in parallel, so R7 is equals to 1 over R2. What is R2? 2 plus 1 over R6, which is 9, correct? Inverse, and the units are ohms. Okay, let's do it. So what do we have? 1 divided by 2 plus 1 divided by 4. Okay, inverse equals to 1.33. So this is equals to 1.333, okay, ohms. Now what do we have? The equivalent resistance is only one, right? Our equivalent is equals to this plus this plus this, because these are now in series. Okay, so this plus what? Plus what is R1 is 2 plus 4, 6, so 7.333 ohms. Also, we can find the current, right? The torque current. What should be the torque current? Well, let's go to Ohm's law to find the current. Is equals to voltage divided by resistance. What is the voltage for this case? Is 10. What is the equivalent of the torque resistance? Gonna be 7.33, okay, ohms. So let's do it. It's gonna be 10 divided by 7.33, okay, equals 2.36, 1.36 amps. 1.36 amps. Correct? So that's the way how we can solve a circuit using only resistors. We mentioned already how we can do it using only capacitors, and also how we can do it when we have more than 2 batteries using the Kirchhoff's rules. Okay, great. And with this we finish the chapter of circuit, and see you in the next chapter. Thank you. Bye.